contro il tempo. Ok. Are you ready?
So,
Great. No? I'm very happy to introduce Stefano Carletta from Sapienza University in Rome, who will speak on long-term capture orbits for low-energy space missions. Thank you.
Excuse me, are you replacing Paolo Tufilato?
Yes.
yes.
Because
For
on
the
the document it's marked Paolo Tufilato.
Yeah, but I was told there was a replacement.
Yes, I'm taking the presentation.
But I think it's
The professor agreed. Okay. So, good morning everybody, and thank you for the introduction. So the work I am presenting here today was developed in the framework of the three-dimensional circular restricted three-body problem, and I am going to refer to it from now on as simply as the three-body problem. And it is aimed at verifying the existence of natural capture orbits about the smaller primary, and we are looking for these orbits departing from trajectories that are asymptotic to libration quasi-periodic orbits. So one question could be, why looking for capture orbits from asymptotic to quasi-periodic? This is because the results of some previous work by Professor Teofilato and Professor Fontaine show that these orbits are of high interest and may give some good hints in defining capture trajectories. We will go in detail on this, and then we will extend the results. Those results were developed in the planar three-body problem, so it was a 2D problem. And we are now extending these results in the 3D with some little differences. And we will see the results in both the physical plane, rotating with the primaries, and in a new Hamiltonian frame. So, to be more clear about the reference frames, we have three representations in this presentation that are the classical physical one, that is 4 state variables, and in the 2D, 6 in the 3D, and they can be reduced by 1 if passing through cylindrical coordinates. In the Hamiltonian representation, we can have less variables, so there's no advantage in this sense, but apparently it is possible to represent the capture condition by just referring to x1 and y1 in both the 2D and 3D problem. This is a sketch of the three representations. We have the physical one, classical one. We can see this is in 2D, so we can see the streaks representing the border of the two manifolds, stable and unstable, converging to the periodic orbit that is in blue. And as we know, to define asymptotic to periodic, quasi-periodic orbits, we have to set two conditions, one on the position, so the point must be inside, in this case, the blue cylinder, and a condition on the velocity, in particular its angle. So if the angle is included within the wedge angle, which you can see in this circle here, we can have transit. Asymptotic 2 are going to be at the limits of the wedge angle, and so we have to see together two plots, two sketches, to understand if the condition is transit or not. This gets much more simple in the cylindrical coordinates, because, as we will see in a while, running inside these tubes that are represented is the same as having the transit condition. I will show you how. And in the Hamiltonian plane, as you can see, there's again the problem of the double representation, the circle for the periodic variables, and the plane that, if we prove that, it can be used for analyzing the capture condition. So we start from the cylindrical representation used in the planar model, and we would work on it by using Birkhoff's equation, reducing from 4 to 3 the state variables, and making some transformation to cylindrical coordinates. So x, y, and z can now be represented in a 3D space, because the maximum that we can represent. And the manifolds that are here can be seen here as tubes. So again, running inside the tube defines the condition for transit. And the tube itself is a characteristic for asymptotic orbits. Now we can see that two tubes representing two manifolds, they intersect either multiple times. And at the intersection, this is an interesting region because something interesting happens. That is, the common region here is temporary capture orbits. It represents the region of temporary capture orbits. And we can see a sketch here where there's a section of this intersection, and the color points, they represent the initial states considered and propagated in the planar problem, and we have a color bar representing different times, different capture times. This is in accord with Conley's theorem that is at the boundary of this region, so where crossing asymptotic orbit exists, near any such there is a capture orbit. Now, this theorem holds in the 2D. It was developed in a 2D, in the planar case of the three-body problem. We want to see if some extension to the 3D problem it can exist. And this is in particular a planar long-term capture orbit, for 8.5 years for the Earth-Moon system. So we have to develop the 3D model. We start from energy. We know that the region, the so-called equilibrium region by Conley, is defined by this hyperboloid, this equation, and it just represents the linearized version of the neck of the zero velocity surfaces. In particular, we are focused on, it works for any collinear libration point, but we are focusing on L1. And again, since we develop this problem in the physical representation, we have two conditions to set. One in position, x, y, and z. So we move from, do you remember the planar case? It was you have to be inside the strip. It becomes you have to be inside the cylinder. And in particular, the asymptotic 2 cylinder is the blue one. This is a sketch of an initial state. Plus, we have a condition on the velocity that is represented in the 3D by two angles. So it can be sketched by a sphere of the cosine directors. And this is the region of the velocity. Inside these regions, so from the center to a point inside this region, there's transit. The limit region, so the blue circle, is asymptotic 2. And again, we have the problem of the double representation at the same time. If we look at the linearized dynamic, 3D dynamics, we can see that the orbits that we are interested in are the asymptotic 2 and are those whose alpha 1 parameter, it is one of the coefficients multiplying the aperiodic plus t term. It must be set to 0. So what we do is, defining this region of points with alpha 1 equal to 0, we also investigate what happens inside this region where Quista transits. And we see if there's any change in the behavior in terms of long-term capture. How did we select the points? So we defined that value of x is 0. So the initial states were selected with a fixed value of x. That is just one delta, so a little step beyond where the two cylinders that intersect. So there's no intersection considered here. We are over the intersection. Plus we are in the alpha plane that contains the smaller primary, of course. Given a section of the cylinder like that, so an x section, we have an ellipse like that with z and y directions, and we define a discretization of z going from 0 to the value, maximum value. Then in the linear problem, it just depends on the energy and the masses of the problem involved, so the mean. And then we divided the interval of y into an equal number of points, equidistant points. This is what, for the Sun-Mars system, around L1, what the velocity regions look like. So it's a spherical cup, of course, and we can see red points that are 30 years captured orbits, and paler points, blue or green, that are short-term capture orbits. They are roughly less than 200 days. So the initial states were propagated in the nonlinear, with the nonlinear integrations, and they were integrated for 30 years. So there is a huge difference between the inner part, greenish, and outer part, red. These are two special cases, but of course, this representation depends, so the velocity depends on the position, as I said before. So let's see what happens by changing the position. As you can see here, in this ellipse, we can separate the left region from the right region. That is, so Z is the symmetry plane of the cylinder. So we start from the left and see what happens and if there's any difference. Going from the outer bound to the inner side of the cylinder, we can see that for any given value of Z ranging from 0 to the maximum value, And for any, almost, for the vast majority of cosine directors of the velocity, theta and phi, it is almost every time captured. So what happens going inside? We can see that the red points start migrating from the center to the perimeter, and in the end, when we are close to the center, the captures, they occur in the other region, so for the limit values of theta and phi. Let's see what happens on the other side. This is another representation from the right side of the ellipse. This is just the opposite. We have capture just for zeta equal zeta max, and there's some little like intention of capture on in this border of the velocity region, theta phi. But if we move again from the from the outer surface to the center of the cylinder, we can see that this capture region extends up to the perimeter of the velocity region. So if we look at the center, in the end, we can see that captures at the center of the cylinder for any given value of z excluding zeta equal zeta max, they are concentrated, they are more probable in the outer region. So for the limiting values of theta and phi. This is a representation in space, and we want to introduce this parameter here, that is alpha 1 over alpha 2, remembering that alpha 1 and 2 were the two coefficients multiplying the aperiodic terms in the linearized model. It is possible to see that for values of y that are belonging to the minor half plane, so the left half plane of the cylinder, and for values of alpha 1 over alpha 2 closing to 0, the capture conditions are almost focused in that region for any value of z, again excluding zeta equal to zeta max. This is another representation that includes the values of theta and phi, and this is useful for seeing that again alpha 1 over alpha 2. It gives us some good hints in finding capture orbits because most of the red points are concentrated in the plane of alpha 1 over alpha 2 equal to 0. Finally, we go to the Hamiltonian representation. So we linearize the classical Hamiltonian. We also make some transformation for having a canonical, symplectic, and real final Hamiltonian function. And we can see that in the Hamiltonian plane, in particular in the x1, y1 Hamiltonian plane, the trajectories, linear trajectories, they are represented as a hyperbola. It is possible for this hyperbola, given an initial point, let's say here, to determine the time for this point to migrate moving on one of the hyperbola it belongs to its symmetric with respect to the bisector. And this time is referred here. This holds for the linear, but we want to see how these things evolve in the nonlinear. So using the results from nonlinear integrations and representing them in the Hamiltonian plane, that's what we obtain. Here I'm showing you the results from the left half plane of the cylinder, so close to the axis, to the x-axis. You have the reference to the physical plane here. This is the high distance view, and this is a little zoom in. So we can see that the captures are at the beginning almost everywhere in the region in the x1, y1 plane, and then going on, so moving to the center of the cylinder, they collect close to the axis. There's another interesting thing, that there's this little branch of red points that is by chance coincident to those points whose value of alpha 1 over alpha 2 is not equal to 0, but it's the smaller value, the smallest value except 0, of course. So again, it seems like that's a good indicator for capture. So what we can see here is that using the Hamiltonian representation to simplify looking for capture solutions, capture initial states, we're just looking for them on the x-axis, x1 axis. If we now match the, let's say the capture time, there's not real capture in the linear model, but the time to migrate to the smaller primary, with the capture times inferred from the nonlinear integration, we can see that there's good matching between the two equations. And again, this plot includes T star, the color bar represents the time from the nonlinear model, And we have in the x-axis the ratio alpha 1 over alpha 2. So it means that apparently alpha 1 over alpha 2 is a good indicator again. So, to conclude, we have seen that we have looked for capture orbits, natural capture orbits, starting from asymptotic, from trajectories that are asymptotic to quasi-periodic, libration quasi-periodic orbits. And we have extended, we have made numerical simulations in the 3D using the circular restricted three-body problem. The numerical analysis showed a good agreement with what was discovered, what was verified in the planar case. So 2D and 3D have some points in common, which was not trivial, but this is a numerical evidence. Plus, we can see that using the Hamiltonian representation, probably both the representation and the research for capture orbits, it might be simplified. So future works aim mainly in go further into this point, using the Hamiltonian coordinates and investigating more them, if they are really that useful. And plus, clarify the possible relations between the homoclinic orbits and the long-term capture, because that could give some more analytical eventually, or evidence in general, even numerical, that there is a connection between the two, just like it is in the planar case. So we could see if the 3D case can be seen as an extension of some kind of the planar case. And thank you.
Thank you. There is time for one very, very short question. No question, but thank you again.
Thank you.